So when we studied discrete time Markov chains in the first half of this course, there was various bits of theory that we developed in order to study them. So we looked at communicating classes, we looked at periodicity, hitting probabilities, expected hitting times, recurrence, transient, stationary distributions, limit theorem, and the ergodic theorem. And basically we want to develop the same theory for the continuous time Markov jump processes. So the good news when doing this the second time round is most of it is exactly the same, and a few bits are just a little bit different. So we'll be able to get through this much quicker in continuous time. So this section, section 19, and the next section, section 20, will all be about just checking how that theory works in continuous time. And hopefully, if you've understood it for discrete time, it should be much easier this time. So we're going to look at communicating classes, hitting probability, expected hitting time, recurrence, transients, stationary distributions, limit theorem, and ergodic theorem. In continuous time, we don't have to worry about periodicity, which was a thing we had to think about in discrete time. Because in continuous time, because the amount of time you wait in a state can, it's an exponential distribution, it could be any real number, positive real number. That means that periodicity just isn't a thing in continuous time. So that's one thing that we won't have to bother with. That's one way in which, actually, although it might not seem it at the moment, in some ways, continuous time Markov chains are nicer because we don't have this periodicity worry. So, sections 19 and 20 are all that theory. We're going to start with subsection 19.1, where we're going to start off with communicating classes, which is going to work almost exactly the same as it did in discrete time. So here's our definition for communicating classes. We say that a state J is accessible from another state I, and write I arrows J, if Pij is bigger than 0 for some t greater than 0. So note that's exactly the same definition we had in discrete time, except for in discrete time we used n for the time variable. So that was Pij n bigger than 0 for some positive integer n, whereas here it's Pij t is bigger than 0 for some positive real number t. But other than that, the definition's the same. It's can you get there in some amount of time? As before, if I arrows j and j arrows I, then we say they communicate with each other, which we write with the double-headed arrow. Again, exactly as we did with discrete time. This is an equivalence relation that divides us into communicating classes. Again, that's exactly what we did in discrete time. If you want to go back to where we did this in discrete time, just to remind yourself of that, you can. Similarly, we have the definitions of irreducible, closed, and absorbing, exactly the same as we had in discrete time. So the only difference is we've changed n to a t. Note also that all these definitions about things like communicates with and accessible with and irreducible, they're all about can we get from I to j. Nothing here has anything to do with how much time does it get us from I to j. It's just does there exist some t. So in other words, when we're thinking about whether something's accessible or whether something communicates with, we're not thinking about time. So it doesn't actually matter whether we're in continuous time or discrete time. Right, everything's going to be exactly the same. So to put it another way, Pij t is bigger than 0 for some t is exactly equivalent to Rij. Remember, Rij is the notation we use for the transitions in the jump chain, the one where we just spend time period 1 in each state. If and only if Rijn is bigger than 0 for some n greater than 0, where this n is an integer and the t is a real number. In other words, we communicate in the Markov jump process if and only if we communicate in the discrete time jump chain. So we can just go straight to the jump chain, the old discrete time stuff, and carry on as we did. So let's just quickly do an example, although I think we almost don't need it, but we'll come back to this example a few times in this section. So the example is, consider Markov jump process with this generator and matrix. Q equals -2, 2, 0, 1, -3, 2, 0, 0, 0. Note that as with all generator matrices, the rows add up to 0. We're negative or 0 down the diagonal, and we're positive or 0 off the diagonal. And in discrete time, we often found it was easier just to draw the transition rate diagram, the transition diagram to see what was going on. And the same here, it would be convenient to draw the transition rate diagram. We've got 3 states, 1, 2, and 3. From 1, we go over to 2 with rate 2. From 2, we go back to 1 with rate 1, over to 3 with rate 2, and from 3 we stay where we are. Remember that in continuous time, we don't bother putting the arrows from a state to itself. There's no need. So I think it's like just straight away obvious here, right, what the communicating classes are. 1 and 2 clearly communicate with each other, so that's one class. And 3 doesn't communicate with anything else. So 3 is another class. So we've got 2 communicating classes here. Let us note that this one is non-closed, because we can take the edge out to 3. This one is closed, because 3 can't escape to anywhere else. And so 3 is an absorbing state. And in particular, because this Markov chain has more than one state, it's not irreducible. So again, that's all been exactly the same as was in discrete time. So hopefully that bit of new theory has been fairly straightforward.